So on this slide I want to talk about the concept of launching a satellite. So if you look here, this is a picture of the surface of the Earth, and imagine that a object is being launched horizontally from the surface of the Earth, or maybe just very, very slightly above the surface of the Earth. So that's this mass m, which is initially a distance r sub b, or Earth's radius away, in other words, from the center. And let's say that m is thrown tangentially with some velocity v. And we know from our kinematics that if in such a case, in 1 second, m will drop 5 meters. And let's say in the process it also travels horizontally a distance l. So if it did that, it would be never hitting the surface of the Earth. In other words, it would, as it shoots out in this direction and falls, the Earth's surface is curving away from its trajectory. And so in such a situation, we would have launched a satellite, and ignoring air resistance, this mass m would circle around. And so what I want to do quickly is to figure out, well, what distance L does it have to travel horizontally for the Earth's surface to fall 5 meters away from underneath this horizontal plane? And so what I do there is realize that I have a right angle triangle here. The hypotenuse is the distance from the center of the Earth out to the tip of this length L, which is going to be the Earth's radius plus 5 meters. And then the two legs of the triangle are this Earth radius and this L. So I can write down an expression for L squared using Pythagoras, which says that L squared is equal to the hypotenuse squared, that's RE plus 5 squared, minus RE squared, which is 10 times RE plus 25. And RE is very large. It's 6.4 times 10 to the 6. So I can basically just ignore this 25 meters. And I can say that L is roughly equal to the square root of 10 times the Earth radius. Earth radius is roughly 6.4 times 10 to the 6th. And so if you work that out, you'll see L is about 8 kilometers. And since we hypothesized all of this happening in 1 second, it means that L has to travel a horizontal distance of 8 kilometers in 1 second for this 5 meter falling away from the surface to occur. In other words, it has to be thrown at 8 kilometers per second to launch the satellite. And so it's good to realize here that we have a simple derivation of what the minimum launch speed is for a satellite from the Earth with a horizontal velocity. And more broadly, a satellite is simply a projectile that falls around the Earth, thrown with a sufficient velocity that the Earth's surface falls away from the satellite at the same rate at which the satellite falls towards the Earth's surface. Down below here I have an alternate view using Newton's second law, and here we have a satellite that's going around the surface of the Earth at a radius r sub b, in other words, just barely above the radius of the surface of the Earth. And so at each point, this mass m, which is executing this satellite motion, is going to have a gravitational force of the Earth on it, which by the gravitational law is big G times little m, the mass of the object undergoing the satellite motion, times the mass of the Earth divided by the radius of the Earth squared. And so by Newton's second law, I know that mass times acceleration is equal to the force. And so the acceleration is v squared over r sub b. M times v squared over r sub b is equal to, therefore, this expression The mass of the object cancels out on both sides, and I can now solve this for v. If I do, I get an expression that says that the minimum launch velocity for causing satellite motion at the surface of the Earth is big G, the gravitational constant, times the mass of the Earth divided by the mass of the Earth, square root of that. And so if one puts the value for big G in, 6.7 times 10 to the minus 11 Newton kilograms to the minus 2 meters squared, times the mass of the Earth, 6 times 10 to the 24th kilograms, divided by the radius of the Earth, 6.4 times 10 to the 6th. One comes up with the same 8 kilometers per second that we found with the simple geometric argument above.